Well, good afternoon, everyone. Welcome. Glad to see you all here. This is an exciting week for us here at Purdue, particularly for robotics. We got a number of things going on. Welcome to our National Robotics Week celebration, as it were. We've coordinated a number of things here today that I want to tell you about. Not only do we have our speaker, Professor Rod Brooks here, who I will introduce in a minute, but first, we're also officially using this day and this event to announce the formation of a new center here at Purdue, the Purdue Robotics Accelerator Center, which is officially inaugurated today, as a matter of fact, which is something we're real excited about because it brings together all the strengths that Purdue exhibits and has across 4 different colleges within the university. It's a very interdisciplinary center that brings together the College of Technology, the College of Science, the College of Engineering, and the College of Agriculture to look at different aspects of robotics in the area of what we call co-robots, or we also refer to as robotics 2.0, kind of the next generation of robotics that work collaboratively with humans instead of the old view, what we call as robotics 1.0, of the kind of lights out factories where we separated humans from the robots because robots were doing these dull, dirty, dangerous tasks. That's still good applications of robotics. But what we're looking forward to, and in particular this new center is embracing, and companies like Rethink Robotics, are a whole new set of applications where the robot and the human leverage one another's skills for different applications in healthcare, manufacturing, and even agriculture. These are the types of applications that the Purdue Robotics Accelerator Center is going to be capitalizing on, and not just from the standpoint of long-term research, which of course Purdue is very well known for, but the complete range from basic research right down to deployment, so we can solve applications, mid-term and medium-term, and as well as long-term research into robotics. And as part of this, we're going to open the labs, and part of the National Robotics Week, we're going to add, after the show tonight, I'll give some more examples of, we're going to have a sampling of some of the robotics labs across campus are going to be available. You can stroll by, meet some of the grad students and others involved in robotics research, and it's an opportunity in many cases to get involved in what's going on campus. But without further ado, let me get to the introduction of the main event here today. This is a huge honor for me. It's very difficult to overstate the contributions that Professor Rod Brooks has made to robotics over the years. And I've had the good fortune of knowing Rod for a long time, and we can say that the standard things that are examples of the success he's had. You know, for a long time he's been professor of robotics at MIT. He is a member of the National Academy of Engineering. He started from South Australia, came to Stanford University where he got his PhD. He's held professor positions not just at MIT, where he spent the most time, but also at Stanford and CMU and RPI. Is that correct? No, sorry, okay. Stanford, CMU, he's held academic positions, a number of prestigious places doing robotics. But what's really exciting, I think, about Rod is he really mixes not just the deep research and the science of robotics, but also his projects have really embodied ways to capture the attention of people, to capture the attention of users, and more recently, to capture the attention of funding sources. He has recently raised his new company, Rethink Robotics, which he is the founder of, and you see examples of their Baxter here. has recently raised $75 million in venture capital to bring us this next generation of robotics that he's going to talk to us about. But also, he is co-founder of iRobot, the company that brought you the Roomba that may be running around your living room as we speak tonight if it's jumped out of its charger. As well as neat robotics like Cog that learned like an infant, and a number of aspects, Genghis, which was a crawling robot. But without further ado, what I'd like to do is bring Professor Rod Brooks up and hear what he has to say about the next generation of robotics. Thank you.
Okay. Well, thanks very much, Richard, for that introduction, and thanks everyone for being here. And it's a great pleasure to be at Purdue in National Robotics Week. Purdue's been a place where robotics has been going on for well over 30 years. Lots of great things have happened here. Richard asked me to talk a little about my history, so I'm actually going to talk from early days, Richard, about some of the ideas I've had over time and how they have led finally to Baxter's. You see a couple of Baxter's on stage here, and I'll show you some other videos. Can people see the screen back there, by the way? Or do we need to get rid of these lights? What do you think? Can you see it? Kill the lights. They say kill the lights. I can stand in the dark. It's fine. So while they're trying to do that, I'll tell you where I got started in robotics. This is I stumbled across this book, The Living Brain, by W. Graywalter. He was an American who lived in Bristol, England, and he was a brain scientist, and he had a description of nerve propagation that I read there, and he'd also, back in 1949, built some robots. 1949, which he published 2 articles in Scientific American about. And these robots they had 2 vacuum tubes in them. They used all the non-linearities of vacuum tubes, and as the batteries went down, changing behavior, etc. Very simple by today's standards, but amazingly complex behaviors. He called them tortoises for what they taught us. So back in about 1971, I tried to build a robot based on these ideas. I used transistors rather than vacuum tubes, which didn't have all the non-linearities. And this is the robot after it had been in my mother's garden shed for 34 years. It didn't look quite that sad in 1971. But it could get around the house, it could follow the lights, it could go under chairs with 4 legs and get stuck in there and not be able to get out. And, so it was a lot of fun. I ended up at Stanford doing a PhD, and this sort of set my direction for a while. I did a PhD in model-based computer vision, and you can see, oh, that's really washed out. The bottom left there, on the bottom left are models of airplanes, 3-dimensional models of airplanes, and with a mere 48 hours computation from that image in the top left, we'd go through to what's on the top right and get down on the bottom right there in the green a model of the plane with only 48 hours per image. And so for my PhD thesis, I actually ran it on 3 images. Now, if you don't run a PhD thesis on around 3 billion images these days, you're not really testing it out. But it was about geometry. And so I went to MIT as a postdoc and started working on path planning and trying to apply geometry to robotics. And what you see there in the black are obstacles in 2 dimensions, and there's a rectangular object starting down in the bottom left-hand corner, and this is finding a path for it to move in 2 dimensions amongst these obstacles without causing a collision. And I went on to think about how to get robots to plan tasks and what to figure out how uncertainties, errors in placement of things, how they propagated through plans, and used all sorts of horrible, long, symbolic, algebraic descriptions of the errors and analyzed them. And eventually started to put all this together into a system which used a robot and stereo vision to get a model of the world, a geometric model, and then plan paths. And this is from 1981. This is the stereo algorithm running. I got this from Keith Nishihara. And then, computers had sped up. We had dedicated special purpose processors by this time. And after about 10 minutes of processing, the system was able to plan out a path for that robot arm to avoid the collisions with the obstacles. And then eventually we got it over to the robot. And so the robot was able to move to do a simple screw insertion task, having planned it itself, with about 10 minutes of computation, and was able to get it in there. I won't show you the other examples. But at the time I noticed, man, it takes us, pages and pages of equations to get our robot to do any new task. It takes us lots of computation still on these dedicated complex machines. And, I was actually in a mosquito-infested area at the time. I noticed mosquitoes could fly around really well, and way faster than any mobile robot could wander around at the time. And they didn't have really big computers on board, as far as I could tell. They had maybe 100,000 neurons, which were pretty slow. They're computationally limited. And so they didn't have much computation, but they were able to act much better than any robots at the time. Right around that time, in 1981, Hans Moravec at Stanford had got a robot to go 20 meters in only 6 hours using vision to get around obstacles. So it seemed to me we were doing things wrong somehow, thinking about too much geometry. And I started to think about how we could model animals, simple animals, insects in particular. I was in the AI lab, so I figured I'd just rename it to be the Artificial Insect Lab. And so that's what I started doing, thinking about how to build robots in different ways and how to arrange their computation. I had this paper, which was actually published in 1986. And for those of you who get bad reviews, these were the reviews of this paper. I would suggest the author wait until a more complete version is implemented and tested before resubmitting. And the other review said it's in a tender stage of development. But somehow the editor liked the paper enough and got it published, and that's what made my career. So, there are bad reviews. Forget it. Just keep going. Things work out. But from this paper, I worried about having multiple goals, how to have high-priority goals while servicing low-level goals, how to deal with multiple sensors. And as soon as you have more than one sensor, you're going to get conflicting information about the world. It's going to be inconsistent. What if some things fail? How do you keep it robust? You can pull a leg off a beetle. I don't recommend doing that, but if you pull a leg off a beetle, the beetle can still run. It can lose sensors, and it still operates. And I wanted to be able to add new sensors and add new processor power and have the robot get better. So I changed the way I thought about intelligence. Instead of sensors going to actuators going via perception and modeling and planning and task execution and motor control, I sort of cut it up orthogonally and into capabilities. First thing is get the robot to be able to locomote, then get it to avoid hitting stuff. And when they're both running, then you can get it to explore. And you don't have to worry as you're exploring about hitting stuff because that lower level behavior is still running. So the idea was to add new capabilities one after another. I called this subsumption. And I thought of this as sort of recapitulating evolution at a sort of scientific American level of resolution, where you connect sensors to actuators with a little sub-brain, and then you add more brain that does more connection of sensors to actuators, etc. And out of that, each layer has a little bit of perception, a little bit of planning, a little bit of action, and out of that you get a global behavior. So I did this for a few years with this architecture. Oh, I'm going to skip this slide. I've got too many slides here. Sorry, I should have got rid of that animation. And so putting a layer to get a robot to wander around without causing collisions of little tiny finite state machines talking to each other with messages, then adding a little bit more to make it wander and explore, and then adding a little bit more to get to goals that it saw in the distance. And I built a robot back in 1984. I also had a simulator. And this robot was named Alan. It used sonar and cameras. And when I put this all together, this was the robot avoiding obstacles. It sat still until an obstacle came near it, and then it would go away from it. And then another obstacle got in the way, and it would stop. And so this was able to operate not in the order of meters per hour, but in meters per second, or meters per minute certainly, so much faster than other mobile robots at the time. People got very upset with me because it didn't have much detailed mathematics describing how it worked. It wasn't a real paper without lots and lots of equations. But I was sick of equations by then. I was a math major as an undergrad. So adding a planning layer, here it's going to try to get to the far side of the room, and an obstacle appears dynamically in its way. At the time, all planners were for static situations without dynamic replanning. And it tries hard, and then eventually it manages to skirt by the obstacle. And if the obstacle moved in the meantime, it would capitalize on that in real time and gets around the obstacle, and off it goes. So I was building mobile robots, looking at this architecture which is based on insects. And then I thought, well, let's make the morphology just like insects. And as Richard pointed out, this is Genghis, a six-legged rover, which was able to scramble over rough terrain. Also around that time, in the late 80s, I built my first vacuum cleaning robot. Wasn't too well designed in that it sucked all the dirty air past the computer boards, which wasn't a great feature, but we'll get back to it. But with this six-legged robot, Anita Flynn, one of my students, and I wrote a paper for the Journal of the British Interplanetary Society. You might ask, why did we publish in the Journal of the British Interplanetary Society? Who could resist a journal with that name? I had to have a publication in that. And it was the same journal the idea for communication satellites had first been published too. So we said, instead of having a big robot that NASA was planning on sending to Mars at the time for a $12 billion mission, let's have little tiny robots that are not so expensive, so if you lose them, you don't worry too much. So it'll be faster to develop the mission. It'll be cheaper because you only have a lot less launch mass. And instead of making them servo-controlled from the ground, let them be autonomous. That's the out-of-control part in this fast, cheap, and out-of-control. And we worked with NASA and tried to get them to adopt this idea. And they started a little tiny project out at JPL with the robots they called Rocky, Rocky 1, Rocky 2, Rocky 3. And Colin Engel here on the left was my student at the time. He went out to JPL for the summer and got them going on that. But it was just a back burner project. Colin came back to MIT, and we decided we were going to do it ourselves. We were going to send robots to the moon and Mars ourselves. So we started a company which became iRobot. It was called iRobot. And by 1993, we had convinced the Ballistic Missile Defense Organization to do a test launch of one of our rovers on a brilliant pebble. This is at Edwards Air Force Base. The sound should be on now. Is the sound on?
Avionics away. 8. Photo on.
So we've got a brilliant pebble. It has enough delta V to get from lunar orbit to the surface of the moon. But here we're doing a test in Earth gravity of it doing a soft landing. The robot has been inside this vehicle for 4 days with no ground communication, totally autonomous. It does a soft landing. It boots out the container, which is gravity loaded so that if it landed on rocks, it would right itself. And then you'll see the rear leg of the robot on the right unlocking itself. It realizes its mission has started. It's undoing this canister, and now it's going to stand up, and we're going to launch this and have it land next to the Apollo 15 lander and do some metallurgy 20 years after it had been on the surface of the moon. That was with the Ballistic Missile Defense Organization. When NASA got wind of that, they said, no way, you can't send a rover to another planet. We're in charge of not doing that. And there was a big fight. And then Dan Golden, the administrator of NASA, said, oh, we've got this little tiny project out at JPL, building robots called Rocky. And we're going to land a lander on Mars in a couple of years. For $25 million, I'm going to add a rover to the Mars mission. And that's what he did. He put Rocky 6, which had come out of Colin's project. Colin is the CEO of iRobot. And it was a $25 million marginal cost. And it was launched on December 6, 96, landed on Mars on July 4th, 1997. And the one on the left is the one back at JPL. The one on the right is a picture of Sojourner on Mars in 1997, and it operated out until Sol 84 days, Sol 84. And you can see it close in, and the bottom, right in the middle, it's off in the distance from the lander. So we got our behavior-based rover running on Mars, and we effectively got a robot to another planet. Of course, that was our business model said we were going to do it. Instead, NASA did it, so we had to find other things to do. And we searched around and got lots of things wrong, but we went back to vacuum cleaning robots and ended up building the Roomba, which is now 10 million of them have been deployed. And about 12,000 ground robots in the US military have been deployed in the last decade, about 5,000 of which are from iRobot. So these ideas worked out pretty well in terms of getting them into practical robots. But then, while I was doing that at iRobot during the 90s, in my lab, I made a conscious decision to switch to humanoid robots, so it would be distinct from my company. And this is the robot Cog, and Cog tried to emulate parts of the vision system. This is it saccading, and then moving its head while its eyes are looking at that object. And when we just added little parts of the human visual system, it started to be eerily lifelike. And it surprised us, and it surprised people in the lab. So the grad students who had got the robot to do this started putting up barriers in the lab so the robot couldn't see them. Not because they thought it was invading their privacy, but they'd be sitting there at night, someone else would be using the robot, and the robot would look at them like this, and they couldn't, even in their peripheral vision, they had to look up. So one of the things we found was it was very easy to have social interactions with these robots. We didn't have to have much sophistication. And we used something called series elastic actuators, and we were able to do tasks which used force and had to be compliant in the world with fairly simple controllers. So there's the robot. Do we have sound? Maybe. There's the robot doing different sorts of drumming and then learning to drum in phase between the two arms, etc. And the key here was to use series elastic actuators. I'm going to get to the next one. It gets worse. Series elastic actuators, which were co-invented by Gil Pratt, who's currently running the DARPA Robot Challenge, the DRC, and Matt Williamson, who works at our company. You'll see a young Matt Williamson here. And here it's doing the slinky, just measuring those very small forces and being able to feed back between them. Here it's got a pendulum, and it figures out the natural frequency of the pendulum. Here it's turning a crank, again, just by feel and force feedback. So that was fun. We developed that for many years, and that ultimately led to this robot, Baxter. And I'll tell you how we got directly to Baxter in a second. This is, by the way, is in a plastics factory in Connecticut. The person there is Mildred. Mildred has worked on the line in that factory for over 25 years. She had never seen an industrial robot, never seen a robot before, but an hour after Baxter was first set up in the factory, she had trained Baxter to do a simple task that was normally done in the factory. And so Baxter is meant in its day job, which is distinct from its academic job here, in its day job is meant to be operated in factories and small factories and have ordinary factory workers be able to train it to do tasks. Well, how did I come to this? Well, the Roomba, 10 million of them, have been built in China. And I'd spent a lot of time on Chinese production lines. These are people in China building robots. Very simple fixturing, very simple operations. But I came during the whatever we call them, the zips or the aughts, to realize that our current outsourcing of manufacturing to China was not going to last forever. In February of 2012, ABC Nightline had a story about an iPad and pointed out that it's touched by 325 pairs of hands in building an iPad. That's a lot of human labor for our consumer goods. The stuff we buy, our consumer stuff, is still made by hand largely, which is sort of surprising when we've got the complexity of our information systems all digital and the internet and communications, but the physical stuff is still largely done by hand. In fact, we've been making stuff in factories by hand for 234 years. We've been using first steam power and then electrical power to do the work part, but it's by hand has been steering that power towards production. People, often say U.S. manufacturing is down the hole. Well, that's just not true. U.S. manufacturing has increased, productivity has increased faster than other productivity for 60 years. U.S. manufacturing output has increased by 3.7% per year for 60 years. That's a pretty good, exponential over 60 years, with mostly flat employment. You see that the red is the employment. It went down in the aughts, but it's starting to creep up. About 600,000 jobs in the last year or so added to manufacturing. And the way we've got that, but the way we have gotten that productivity increase is largely by outsourcing the volume stuff and keeping the higher value add stuff. I was with sitting with I've forgotten his name now, Craig. He was CEO of Intel. Craig, not Barnett, Craig B. and at a panel at the National Academy, and he said, yes, the US is going to win in manufacturing by finding the things no one else in the world can build, and we'll build them. And so that lets you build jet engines, and jet engines are coming to Lafayette, I hear, from GE, which is great. But there's a lot of other stuff we buy every day, and we've sort of outsourced that to low-cost labor parts. But we've been chasing low-cost labor. So right after the Second World War, a lot of stuff for the US and Europe was made in Japan, whose economy had been devastated, but there were a lot of entrepreneurial people there, and they started building stuff for the US and turning small companies into global brands like Sony and Sanyo, et cetera. As the economy recovered, cost of labor there went up, which is natural, and so some OEMs like Samsung and LG started operating in Korea doing the manufacturing, and then they became global brands, and labor costs got too high. So they moved to Taiwan. Taiwanese companies, many have become brands. Acer is one of them, but other companies like Quanta Computer, Delta Electronics, et cetera, operated in Taiwan until labor costs got too high, and then they started moving their manufacturing operations to China. By the time in 1997, I was doing my first manufacturing in China. I was actually, I built, Baxter's not my first humanoid robot. My first humanoid robot was a doll called My Real Baby that we co-made with Hasbro, about 100,000 of them. I won't show you a picture. But we made that in southern China. But it was too expensive in 1997 to do the plush, the sewing, in China. We already were doing that in Vietnam. And that's where things have gone, as we've seen labor costs go up in China as the standard of living is raised. And then we just sort of run out of places, because already Thailand has had an industrial revolution brought about by Japanese companies moving their manufacturing to Thailand already. So we've been chasing low-cost labor, but I don't think we can continue to chase it. All places the boats are rising and the standard of living goes up. And when the standard of living goes up, people don't want to do those really mind-numbing assembly jobs in factories, and we see that happen. We see the implications of that. This is the cost of labor in 2003, 2004, and you can see the history of manufacturing around the world, starting with Germany, then France, the United States, Japan, South Korea, Taiwan, Mexico. Back then, labor was 90 cents an hour in China. It's now about $3 to $4 an hour, and guess what? People don't want to have lousy work conditions, so we see all the work problems that are at Foxconn, because when people are getting paid more, they're not so scared of losing their job. When the number of 19-year-olds starts to drop, they're more confident in their jobs, and rightfully, in my mind, they want better work conditions, and so we see it harder and harder to get people to do really horrible jobs. So it seemed to me that we needed to break out of making cheap stuff by hand, and there were lots of reasons to want to bring manufacturing back to the US, back to Europe, back to Japan. Part of it is responsive short supply chains. But also, I think we've started to realize over the last 20 years is as soon as you start outsourcing your manufacturing, you outsource your innovation also, and you lose your innovation. Because it's just too hard to get back and forth to the other side of the world. So you let the great talent there do the engineering, and before long you're not doing the engineering in your home company, and you've lost control of the product. So let's use robots instead of people. Robots have been in factories since 1961. The first ones were built by a company called Unimation by Joe Engelberger, who's still alive. First installed in a GM factory in New Jersey in 1961. But back in 1961, computers were really big and expensive, so the robots didn't have computers. They didn't have much in the way of sensors, and they did the same motions repeatedly, again and again and again. And still, a lot of robots today, a lot of industrial robots are doing the same sort of thing. They're just a robot arm. They do have microprocessors around now, and the microprocessors doing complex things like running Kalman filters to model the wear on the gears and make them accurate. So these robots are fantastic devices. So you can run them for 10 years without servicing, and they'll follow a trajectory to an accuracy of 0.3 millimeters again and again every 20 seconds for 10 years. But they've been engineered to be precise and repeatable, not to be adaptable, flexible, or easy to use. So robots, industrial robots, only get used in very structured environments. In fact, most industrial robots, 70% of them in the world, are in automobile factories, in the body shop and paint shop. And they don't have built-in sensors, so they're dangerous to be near. They're big, powerful devices. And so people can't work with them, so you tend to have places where it's all robots, or in final assembly, it's all people without robots. They don't mix very well. Since what they're good at is following a trajectory accurately, most applications out in the world tend to require incredibly expensive systems integration, safety systems, programming of them, specialized programming, and the capital cost of the robot is only a small fraction of the total cost of the system. So the robots you see out in the world tend to be like this. These are building car bodies. They're doing it very well, very accurately, much better than people could do it, but it's all robots, no people, and this whole system is guarded so that if anybody goes into that area, the whole system shuts down. So you better make sure those robots are 100% reliable all the time, because you can't have people going in and fixing stuff without shutting down the whole system. And in my view, what's happened is we've continued to build industrial robots in the old way, where they're hard to use, without the sensibility that we've applied to our consumer devices. These are really complicated devices, but they're easy to use. They've been made easy to use. If they were, and I used this, I told Richard this example earlier today. You know, this has got a Linux in it. So does an Android. If you jailbreak this one, you can type a command line, a Unix command line, and make a phone call. Well, I could do that, but I wouldn't be making calls all the time if I had to type a Unix command line. We made these easy to use. We haven't made our industrial equipment easy to use. So to me, it was important to make industrial equipment easy to use, because there's over 300,000 small manufacturing companies in the US, almost none of whom have robots, because they're just too many barriers to entry. You need specialized programmers. You need all sorts of extra equipment. So that led to Rethink Robots. I call them production robots. They're not industrial robots. They're a different category. It's venture-backed. We started in 2008 and shipped our first product in 2012. We were very secretive about what we were doing, although when we put out our new logo, I thought everyone was going to know exactly what we're doing. The logo's in the top right corner there. It's a guy with an orange shirt and a round head next to a red robot with a square head. And this is a real factory worker in a factory that makes gearboxes for Harley Davidsons, actually. He wasn't wearing the orange shirt, but I think Sue gave him the orange shirt so that we could take this photo of him. So we've been shipping these robots for just over a year. You can see them up on stage. They have these series elastic actuators in them, which let them sense force. And so whenever you grab a robot arm, or grab the arm here, it goes into what we call zero force gravity compensated mode. So you can just move the arm around as as though it's floating in space. If you don't grab it down there, it's sort of springy, and it's springy not because of the springs in the series of elastic actuators exactly, although it's part of it, but it makes it safe to interact with. I'm not going to, normally I would have this is set up for a demo. Normally I'd have this swinging wildly and I'd put my head right in the way of the robot arm. I don't recommend that with an ordinary industrial robot. But it senses force. Here it senses the force and tries to make zero force on the end of the robot, on the wrist there, while compensating for gravity. So the way that you train this robot is by grabbing its arms and showing it things. Oh yeah, by the way, there's a camera in each hand there. There's a rangefinder. There's accelerometers in the end. So it's sensor-rich, and it's able to see objects in the world, which we'll see later. So we think this is a sort of new category, a different sort of robot. In the same way the Roomba floor cleaning robot was different from what was out there before. Our idea with this, and we haven't completely gotten there, is that there should be no integration. You take the robot out of the box, it's got cameras, it's got force sensors, it's got other sensors, and it should just operate out of the box. Our goal has been to have it working in under an hour. Occasionally happens. It does require, in practice, a little more integration than that. But you don't program it in code. You train the robot like you teach a person. You show it what to do. That's with our manufacturing software, which is not on these robots. But the idea is when the robot's finished some task that you might operate on for a few hours, you move it over to another line, have it do something else, is the idea. It's aware of its environment, adapts automatically to some changes in the environment, and most importantly, no safety cages. It's safe to be close to. And we view this as a hardware platform, just like Apple, say, or Samsung, views this is a hardware platform. That's the phone. But iOS is a software platform that happens to run on here, happens to run on iPads, happens to run on other devices, the iPods maybe. And you can upgrade the software without upgrading the hardware, but you increase the performance. So when I went from 6 point something to 7.1 on here, or 7.0, it was a completely different experience with all sorts of new capabilities. So when a new software release comes out for Baxter, it really improves what it can do. So earlier this year, we increased the speed of the robot dramatically. We've got a new release coming out in next week, I think, of software which increases the speed even more and increases the accuracy of how well it can go to a position, and decreases some of the sloppiness in the motions, and lets you train more complex tasks. So software is independent of hardware. They're two product lines that can change over time, but they're independent. That hasn't been the way we've thought about robots before. This is the series elastic actuators I told you about, where there's an elastic element in series with the motor, gear train, and load. Lets us control force and stiffness, protects gearboxes from shock, etc. And then we have this. I can't show this to you on this version of the software. Imagine this is a cup, okay? This watch. Imagine this cup, and they're not running the manufacturing software. But when you grab this, and I don't think they're. Whose demo is this? If I press the buttons, is that going to cause any problem? Can I experiment? No, it's not running. Okay. When you press this lozenge button here, it changes the state of the gripper. So suppose this is a cup, and I bring the fingers down, they're closed, and I press the lozenge button, they'll open, it'll feel a force, and it'll say, the person must have meant they wanted me to pick something up here, because there was nothing in my hand before, now there's something in my hand. And the way to do this pickup was by opening my fingers. Whereas if instead I'd brought the hand down with the fingers open and closed them, it would have inferred, this is a pickup location, but here I'm supposed to pick up by closing the fingers, and because that's what happened, and I felt the force. Now, we could have made the user interface be a menu-driven thing, saying, now I want to do a pickup, click. Now I'm going to choose which way to open or close the fingers to determine what sort of pickup it is, a couple more clicks. Instead, we just show the robot what we're doing and let it make those inferences. So in the manufacturing version of the software, the face, why is that face there, by the way? The face is there because in the manufacturing version of the software, the eyes glance where the hand is about to move so that people who are working around the robot aren't surprised when it moves. It's not like it's looking over here and does that. If it's going to do that, it looks over there first and then does that, so people feel safe around it because they know, and they pick this up very quickly. They pick up that it's going to telegraph to them what's about to happen. So as you interact with the hands, it will infer things like a pickup there. And this is a map it shows of its workspace, with the blue being the right arm, the green being the left arm. It will infer there's a pickup. You can go in and say, I want to add a description of the object from the cameras by pressing the eye icon. It will infer put downs. It will do all sorts of things, and you can tell it whether it's static or moving, etc. So here's training a blind pick and place, just a very simple task. This is actually version 1.0 of the software. So here she closes the fingers. It infers that it was a pickup, puts that icon there. Then she opens the fingers, infers, nods, infers that was a put down, and that's a pick and place task where it's not using vision at the moment. So she's got to put the object where it's going to go to where she showed it, the pickup. It goes down, closes the finger, feels it's got the object, moves it over. If she stole the object from it, would go back and look for another one. That error recovery is built in. This arm's in the other way. I'm going to move it out. It's a little puzzled. It's figuring stuff out. It's optimizing the program slightly, puts it down, and has done the task. And here, and it's going to be whited out on the screen. I'm sorry about that. Here's the same task showing what appears on the screen. That's all white, isn't it? Okay, I'm just going to let this run because this next part is what I want to show you. But it's nodding. It's putting up the symbols of a pick up and put down. But from zero to a simple task is easy. Simple things are simple, but you can go and drill down deeper if you want to do something more complex and say, oh, by the way, when you're moving from the pickup location to the put-down location, I want you to be 22.5 centimeters above the table. And here she's just in the way as, oh, it hurt her. It hit her, didn't hurt her, sorry. It's safe to be around and work in close proximity. Here's just showing you some vision. He's trained it to pick up these cups by putting fingers in and opening outwards, and he's just showing it where to put these, and then you'll see it servoing on that. Doesn't know, you don't have to tell it what the velocity of what the servo is, the direction. If you change those, it adapts, uses a KLT tracker, and is able to go and put these objects down. It's looking around to sort of indicate what it's doing. And this is a really dumb task that it's doing here because with the other hand, you will notice in a second, it's picking up the objects from somewhere and putting them on the conveyor. But it was just to demonstrate. So here's the robots working in a factory. This is kitting plastic furniture, the sort of plastic furniture, sort of shelves you'd put down in your basement. This is kitting that. You see the humans working closely in close to the robot. Two robots there working. Now there's some interesting things here. As we zoom in on the robot on the left, you'll see its right hand has suction grippers made out of plumbing materials. What happens is people in the factories build custom hands for it. We don't have general purpose hands at this stage. The left hand that you see in the top right hand part of the screen there has fingers made with a 3D printer, an electric gripper. So that's what we see all the time. People custom build the end effectors for the task. We do not have general purpose robot hands that are good for general purpose tasks. I'll get back to that in a minute. And this is just to this is a Vine video from Take Your Kid to Work Day last year. This is the children of one of our people, and our engineers are happy to let their kids be in close to this robot. They don't feel the robot's unsafe. Without any instruction, the kids, of course, went into the menu system, tried to get the robot to do something. They tried to train it to do something with no training themselves. They didn't, the robot thinks it knows what's going on, but it's a little confused by what they trained it. But the point here is it's safe to be around. We feel good enough about the robot to let our young children play in close with the robot. So I just want to talk about metrics. One of our something that comes up with this robot all the time is people think, it's a robot, therefore I should apply my conventional metrics to it. One, you've got an industrial robot in your lab. How high can it jump? He sort of snickered. It's a silly question. How high can your industrial arm jump? It doesn't make sense. But by the way, Mark Rabot at Boston Dynamics is very proud that his robots can jump 4 meters because they jump over a fence and they're spy robots. And so that's the right metric for his robot. It's the wrong metric for an industrial arm. Honda, with their Asimo robot, have announced that it can jump, I think, 1 millimeter. They're really pleased by that. Sorry? So conventional industrial robots have had metrics of precision, repeatability, and speed. That's what makes sense for them. We think Baxter has different metrics that are important. Adaptability, flexibility, ease of use. Now, throughput is important, but that's not the same as speed. Because if you're getting the robot to do a task for just a few days, it's the total amount of time it takes to integrate it, train it, and do the task, not necessarily how much takt time on each individual operation. If you're getting an industrial robot to operate for 3 years, it's all about how fast each operation goes. So throughput rather than absolute speed is important. So it's a new category of robot. We're trying to make it interact with existing machinery more and more, making it just easier to roll in and have it do existing things. But there's some other stuff going on in the world, which is changing, I think, manufacturing. This is the maker movement. In the top right corner there is Chris Anderson, who used to be editor-in-chief of Wired. Before that, he wrote for The Economist. He started playing around on his dining room table with quadruptors, and before he knew it, he had started a company called 3D Robotics, quit his job at Wired, and has become one of the darlings of the maker movement. He's in Shenzhen right now at the Maker Fair in Shenzhen, which was yesterday, I believe, showing off his wares. The bottom there are these 3 guys with a wooden 3D printer. Oh my God, a wooden 3D printer, what sort of junk is that? Well, they sold it for $480 million to Stratus, I can't remember the name. This is MakerBot out of New York City. So there's some real stuff happening in this maker movement. I think very similar to what happened in Silicon Valley in the 80s, where the Homebrew Computer Club was saying, we're going to build our own computer. And if you saw the original Apple, it had a wooden case too, which was pretty goofy. So there's stuff happening with easy-to-use robots. There's stuff happening with maker spaces. As these 3D printers get better and better, there's going to be all sorts of stuff. They'll be able to be used to make tooling. When we can mix plastic and metal, the 3D printers are going to be better, and maybe we'll get them high speed. I don't know whether they're ever going to be volume production, but in the future, production may operate not such in volume levels. Oh, let's go back, as in the past. And on the right there is what I call super CAD. Right now, our CAD tools are often used in a WYSIWYG way. What you see is what you get, which is like a Word document rather than like a LaTeX document, which is programmed and tells you how to structure it. So as our CAD tools become more parametric and add more manufacturing information into the CAD tool itself, I think we might end up seeing a different sorts of models of manufacturing. I don't know what the models are going to be exactly, but here's just a little idea. This is a current model of manufacturing. A product company sends a design off to a big factory in China. They build the product, they ship it to the US, it goes to big box or virtual retailers who then get it out to the customers. In the future, it may be a little different. Maybe the product company doesn't send the design to a factory in China, doesn't own the design, but sells the design directly to the retailer. The retailer buys the design, not the product. Then the retailer geographically puts out for bids to little factories all over the country, which may be run by makers, may be run by different sorts of businesses than we have now. And then they make the product locally. Instead of shipping it all over the country, perhaps, then they send it out to consumers, either through e-commerce or maybe to local brick and mortar stores. I don't know, but a different sort of model. And could we really change manufacturing and change the models of how companies work? Well, a friend of mine at MIT, Deb Roy, 4 years ago started a Twitter analytics company, which he then sold to Twitter right before the IPO. Rumor is it was $100 million. 5 years ago, did any of you know that we needed Twitter analytics companies? No. So as the technologies change, the roles of businesses and who are the business players and what they do change, and it's an incredible place, I think, for entrepreneurial activity from students such as yourselves at places like this who have the training to come up with new business models and get in there and do new sorts of things. But meanwhile, I think our world is driven by another issue. In China, the US, Europe, if you look over the last 40 years, the percentage of adults who are working has gone down. But that's about to change drastically because the baby boomers are about to retire. In China, it's slightly different reasons, but it also is happening. And so the percentage of adults that are working is going to be much lower, and the number of elderly people is going to be much higher. So we got the ratio of working age people to elderly people is going to go down dramatically. So who's going to look after me when I'm old? Who's going to provide me services? You know, I'm going to be sort of stuck with no one to provide me services. Now, I think robotics in general is going to help here. People talk about self-driving cars. I saw some work here today about self-driving cars or augmented driving for cars. There we're turning cars into robots, and that will let the elderly, like me, drive safely much longer because the car is much smarter about driving. But I think there's going to be a real pull for technologies, physical technologies, that let the elderly maintain control of their lives and stay in their own homes longer so they don't have to go into managed care. And I think it's going to be a tremendous pull. Which brings me to Baxter Research Robot. We're a little company. We've been building a robot to go into manufacturing. But when I looked back at how the self-driving car had come about, I realized it was because in the late 80s and early 90s, we went from a handful of research labs in the world that had mobile robots to hundreds of research labs that had mobile robots, because little companies started selling mobile platforms that universities could buy. And so by the mid-90s, we had, instead of maybe 10 or 20 people working on navigation of robots, we had 5,000 people working on navigation for robots. And out of that came a formalization of something we didn't know needed to be formalized, called simultaneous localization and mapping, SLAM, which led to the DARPA Grand Challenge, self-driving cars, which led to the Google car, et cetera, which led to all the driving features that are being put into high-end cars right now, and we know they'll trickle down to low-end cars, just as anti-lock brake systems did over a 20-year period. So it was by going from, instead of a few people working on a problem, to thousands of people working on a problem, that's when the good ideas are generated, and that's when progress is made. So last May, we decided to put Baxter out as a research robot, and different than previous robot arms, because the safety behaviors that are in the robot arms are on all the time, so it's safe for students to work around. And my hope is that all of you out there working with these robots, well, my hope is that you'll make my life more comfortable when I'm older, but more specifically, do better than what we're doing at Rethink Robotics, because we're just a small company, and make robots easier to use, make them smarter, add new sensors to them, give them better perception. Here's a really important one: develop new hands. And there's an interface at the end of the wrist there, so you can put your own hands on there. I'm hoping by having lots of people with safe robot arms to work with, we'll see lots of new hands, and develop new application areas. And so I've been here today at Purdue, and I've seen some new application areas. And I think we're going to see some demos of that now. Is that right, Richard? And as they come up for their demos, I'm just going to run this video in the background. This is our last version of the software. Someone said, well, can Baxter make me a cup of coffee? And so one of our application guys who says he told me he's never written a line of code in a morning got Baxter to make cups of coffee. So thank you, and we'll see the demos, I guess, now. Thanks.
Okay, can you hear me now? So the benefit of the Baxter approach is programming by demonstration. The Baxter has been, you guys ready to go? The Baxter is what we call lead-through teaching, where they actually use the robot to observe what the human does. We're looking at actually having the robot look at the human through both sensorizing and sensorizing the human as well as using computer vision. And there's just a very simple task they're going to do here, just so you can see it from far away, is a simple block picking task. They're going to go through a couple operations of actually showing a program being created. So as the blocks are now the invisible feeder operator here we can just ignore, but we have our human user, which is going to demonstrate the task for the robot. And in this case, it's simply doing a simple program of picking up blocks. And in this case, it's a fairly simple task of grabbing just the yellow blocks and letting the other ones go. Uh-oh. All right, well. What are you doing different in this one? Oh, okay. All right, well. Okay, that's good enough, I think. Okay, well, the idea is, again, just showing it a different task and having the robot watching through demonstration that the human is doing, abstract the motions that the human is doing, whether taking the same colored blocks or different colored blocks. And now, what I'd like to introduce another professor. Professor Juan Walks from the Industrial Engineering Department is going to tell us about the Gesto Nurse. Juan?
Well, thank you. So what we have here is a different application for this unconventional robot, the Baxter. We want to use this robot to assist surgeons in surgery. So what we have here is a pair of students, a graduate student and undergraduate student. He's not a surgeon, but he's practicing this task. He's an engineering student. And what we are trying to see is how we can use this robot to assist surgeons by delivering surgical instruments as the surgeon requests them. We are looking into natural interaction. So this is unconventional interaction. For robots, it's very conventional between humans. How surgeons interact with surgical nurses are through speech, through hand movements or gestures, and even through body stance and body language. So we're going to look into those three different modalities: speech, gestures, and we have what we call foot gestures, where you will see there is a dance on dance revolution pad there, and the surgeon is going to use that interface to interact with the robot as well. These are foot movements or foot gestures that the surgeon is using to communicate with the robotic assistant. All right. Sponge. Last one. Okay. Last one? Last one. All right. All right. Well, thank you very much, Richard.
All right, thanks to all of our grad students here and help with the demos. But again, I'd like to thank you for your attention and your attendance. We are doing after tonight from approximately 7 to 8 or 8:30, we're going to have open houses, I mentioned, at the various labs. There is maps out on the table outside the Loeb Playhouse. The laboratories that are open, we have 4 labs that are open this evening, that include the assistive surgery lab, the collaborative robotics lab, multidisciplinary design lab, and the interactive manufacturing lab. And again, these are located in the Michael Golden Labs and in Noy Hall. And find maps out on the table and further instructions if you follow the C3PO and Baxter heads. All right? Thank you very much and enjoy your evening.